Yeah, welcome everyone to a new virtual seminar on geometry with symmetries after a short break for the Northern Hemisphere summer. And today it's my great pleasure to welcome Victor Sanmartin-Lopez from Santiago de Compostela. And he'll be talking about isoparametric hypersurfaces in symmetric spaces of non-compact type in higher rank. So thanks, Victor.
Well, thank you. First of all, indeed, I would like to say thank you very much to the organizers for the opportunity of giving a talk in this virtual seminar on geometry with symmetries. It is a great pleasure for me. And also thank you, Ramiro, for your kind introduction. And concerning my talk, I will present, the main aim is to present new examples of inhomogeneous isoparametric hypersurfaces with non-constant principal curvatures that will exist, that will hold in any symmetric space of non-compact type, provided that the rank is greater or equal than 3. And let me just mention that this is a joint work with Miguel Dominguez Vázquez. And well, I have decided to divide my talk in 3 parts, in 3 main parts. Of course, I will start by introducing the notion of isoparametric hypersurface, which will be the central notion today. And I will also present some well-known results, some classical results related to them, related to isoparametric hypersurfaces. This is to give you some context before presenting our main result, our main theorem. Then I will very briefly establish some notation, some tools concerning the algebraic structure of symmetric spaces of non-compact type, because we will make extensive use of them in the last part, in the main part of the talk, where I will try to give you some hints on how to prove our main result. So let us then start with the central concept of this talk, which is that of isoparametric hypersurface. Well, a hypersurface is said to be isoparametric if it and its nearby equidistant hypersurfaces have constant mean curvature. So as follows from the definition, if you start considering an isoparametric hypersurface and you calculate the equidistant hypersurfaces, what you get is more isoparametric hypersurfaces. And indeed, if you continue with this process, what you get, at least locally, it is a foliation. Indeed, in the context where we study isoparametric hypersurfaces, which is that of symmetric spaces of non-compact type, this can always be extended, in the examples, can always be extended to a singular Riemannian foliation that, roughly speaking, can be of 2 different types. On the one hand, and as in the first picture, this singular Riemannian foliation can be entirely constituted by isoparametric hypersurfaces, by submanifolds which are equidistant, of codimension 1, and with constant mean curvature. Or on the other hand, and as in this second picture, and indeed the examples that I will present today will be of this type, this singular Riemannian foliation will be constituted, of course, by several equidistant isoparametric hypersurfaces, but we will have also an equidistant submanifold of codimension greater than 1. This submanifold of codimension greater than 1 is usually called in the literature as the focal submanifold or the focal set. So I will mention many times in this talk, focal submanifold, focal set. In this picture, of course, this black straight line is playing the role of the focal set. Indeed, it is possible to recover the initial isoparametric hypersurfaces by using the focal set. They are nothing else but tubes around the focal submanifold. They can be obtained by exponentiating the unit normal bundle of the focal set at a certain distance. And indeed, as you see from the definition and these pictures and examples, once you have one isoparametric hypersurface, you have equidistant isoparametric hypersurfaces and eventually a focal submanifold. So it makes sense, and I will refer many times to an isoparametric family of hypersurfaces, meaning precisely that, all the equidistant isoparametric hypersurface and, if it exists, a focal submanifold. And let me also say that homogeneous hypersurfaces are always examples of isoparametric hypersurfaces, or in other words, a homogeneity one action induces an isoparametric family of hypersurfaces. This is because if you consider a homogeneity one action, then two homogeneous hypersurfaces, they are equidistant and they have constant mean curvatures. So in particular, they are equidistant and they have constant mean curvature. So that's why homogeneous hypersurfaces are always examples of isoparametric hypersurfaces. Well, the problem of studying, many mathematicians have studied the problem of isoparametric hypersurfaces, and indeed, there are some spaces where a classification result is known. The first one is the Euclidean space, and here the classification is due to Segre in 1939. Here, a hypersurface is isoparametric if and only if it has one or two constant principal curvatures and it is an open part of one of the isoparametric hypersurfaces of one of these isoparametric families of hypersurfaces. So these are equidistant planes or equidistant hyperplanes. These are concentric spheres, and these are coaxial cylinders. So this black straight line is playing the role of the focal sum manifold. As I said, all these examples have one or two constant principal curvatures, and apart from being isoparametric, they are also homogeneous. So in the Euclidean space, being homogeneous is equivalent to being isoparametric. Another space where a classification result is known is the real hyperbolic space, and this result is due to Elie-Cartan. Here, a hypersurface is isoparametric if and only if it has, again, one or two constant principal curvatures, and it is an open part of one of the isoparametric hypersurfaces of these isoparametric families of hypersurfaces. So, of course, I am using the ball model for the real hyperbolic space, and just for saying something about these examples, here, this kind of orange thing is playing the role of a totally geodesic real hyperbolic space of codimension 1 in the ambient real hyperbolic space. And these green ones and these yellow ones are equidistant hypersurfaces to this one. In this second picture, this black straight line is playing the role of a focal sum manifold, and it is a totally geodesic real hyperbolic space of codimension greater than 1 in the ambient. And the rest and the hypersurfaces are tubes around this focal sum manifold. And here we have geodesic spheres, and here we have orospheres. As I said, these examples have one or two constant principal curvatures, and again, they are homogeneous apart from being isoparametric. So at this point, one may think that isoparametricity could be maybe a nice geometrical way of writing down homogeneity, which is at the end an algebraic concept. But however, and I think it was quite a surprise at the time, there are inhomogeneous examples of isoparametric hypersurfaces in spheres. In spheres, the problem turned out to be much more involved, and there are a lot of contributions to the problem. In spheres, an isoparametric hypersurface has 1, 2, 3, 4, or 6 constant principal curvatures. If the number goes from 1 to 3, so if it has 1, 2, or 3 constant principal curvatures, then all the examples are homogeneous, and they were classified by Elie-Cartan. When the number of principal curvatures is 4, then here is where we have inhomogeneous examples of isoparametric hypersurfaces. We have isoparametric hypersurfaces that cannot be described as the orbit of a Lissau group of the isometry group of the sphere. These are usually called the FKM examples because the most complete list is due to Ferus, Karcher, and Meusner. And here, with 4 principal curvatures, also there is a classification of isoparametric hypersurfaces in spheres. When the number of principal curvatures is 6, then all the known examples are homogeneous, but it is not clear yet if the classification result is solved or not. Well, and I am, of course, talking about isoparametric hypersurfaces and isoparametric families of hypersurfaces. They constitute the central topic today, but I am also paying special attention to their focal sum manifolds, to the focal sum manifolds of these isoparametric families of hypersurfaces. The reason is the following. I said at the beginning that I was going to construct new examples of isoparametric hypersurfaces in symmetric spaces of non-compact type whose rank is greater or equal than 3. And in order to do so, the approach that I will follow, roughly speaking, then I will be more precise, but roughly speaking, I will take a homogeneous submanifold of codimension greater than 1, which is a good candidate for the focal submanifold of an isoparametric family of hypersurfaces. I will construct tubes around this candidate for the focal submanifold, and I will try to understand in which cases or under which circumstances these tubes are examples of isoparametric hypersurfaces. Well, after this vague procedure that I have just described, I think there is a natural question arising, which is which kind of submanifold is a good candidate for the focal set of an isoparametric family of hypersurfaces? Well, in order to address this question, I will introduce this theorem due to the mathematicians Ge and Tang, where they at least give a partial answer to this question I have just posed. And I will also use this result to introduce the notion of austere submanifold, which will be important today. Well, the first item of this result says that if you have an isoparametric family of hypersurfaces with a focal set, with a focal submanifold, then this focal set has to be minimal. So a good candidate for the focal set of an isoparametric family of hypersurfaces should be at least minimal, otherwise you will not succeed in the construction of isoparametric tubes around it. But the second item contains more information, and it says the following. It says that if you have an isoparametric family of hypersurfaces with constant principal curvatures and with a focal submanifold, then the principal curvatures of the focal submanifold do not depend on the normal direction. And I will call submanifolds having this property CPC submanifolds, submanifolds whose principal curvatures do not depend on the normal direction. Let me maybe be more precise about the definition of CPC. Imagine that we have a submanifold M in an ambient Riemannian manifold. Then at one point we can take a unit normal vector psi, and at the same but also at a different point we can take a unit normal vector eta. Then we will say that M is a CPC submanifold by definition if the eigenvalues of the shape operator with respect to psi coincide with the eigenvalues of the shape operator with respect to eta counted with multiplicities. This CPC is a notion that I have introduced in a joint work with Jürgen Berndt, and this letter CPC stands for constant principal curvatures. But I would like to point out that this is a more restrictive definition than the one that was introduced by Heinze, Olmos, and Torberson a few years ago. Well, the easiest example of CPC submanifold is probably that of totally geodesic submanifold, because all the principal curvatures are zero and they do not depend on the normal direction. But not also that if psi is a unit normal vector to our submanifold, then minus psi is also a unit normal vector to our submanifold. So if M is CPC, the eigenvalues of the shape operator with respect to psi must coincide with the eigenvalues of the shape operator with respect to minus psi, and they are opposite to each other. So in a CPC submanifold, what is happening is that the set, indeed the multi-set of principal curvature, is invariant under a change of sign. And this is precisely the definition of austere submanifold. A submanifold is said to be austere if the multi-set of principal curvatures is invariant under a change of sign. So CPC submanifolds are always examples of austere submanifolds and of minimal submanifolds. But coming back to the result.
Yes, question. So, I mean, these focal are co-homogeneity, codimension greater than 1, right?
Yeah, exactly. The focal submanifold.
So here you also mean that the eigenvalues don't depend on the direction of the normal vector, right? Because the example is hypersurface, the picture, but you also mean that the eigenvalues of the shape operator.
This also holds for codimension greater than 1, yes.
Okay, so it's a much stronger condition then. When it's codimension 2, say that the second fundamental form doesn't depend on the normal direction.
Yeah, okay. Exactly. Yeah, it's a very strong condition. Yes. Well, so coming back to the result due to Guantan, the first item says that if you want to start with a candidate for a focal submanifold, it should be at least a minimal submanifold. But the second item kind of suggests that it may be much better if you start with a CPC submanifold, because then you still have a chance of getting isoparametric hypersurfaces with constant principal curvatures. I mean, with a higher degree of symmetry. So as I said, in a joint work with Jürgen Bernd, we introduce a large family of homogeneous submanifolds, which are CPC, but non-trivial. Non-trivial in the sense that they are not totally geodesic, but they are CPC. We were interested in these examples for many reasons, because they are a nice class of submanifolds in between totally geodesic and minimal. Also because they are related to homogeneity one actions. But we always had in mind, or at least I always had in mind, to try to construct examples of isoparametric hypersurfaces around these CPC submanifolds. Indeed, this seemed reasonable from the following point of view. In all the known examples, in any Riemannian manifold of isoparametric hypersurfaces with a focal submanifold, the focal submanifold is at least austere. I mean, it has to be minimal, but in all the known examples, in any Riemannian manifold, it is always austere. Sometimes CPC, sometimes totally geodesic, but at least always austere. The thing is that I did not succeed with this approach of constructing tubes, at least not yet, around CPC submanifolds. And indeed, despite the fact that I have presented the classification result of isoparametric hypersurfaces in Euclidean spaces and real hyperbolic spaces, which are of course symmetric spaces, I think we are still really far from getting classifications or even from understanding well the problem of isoparametric hypersurfaces if we just refer to symmetric spaces, or in particular to symmetric spaces of non-compact type. Indeed, the only classification in complete Riemannian manifolds are the one in the real hyperbolic space, this one due to Elie Cartan that I showed you at the beginning, and one in complex hyperbolic spaces. And this is a result that I achieved in collaboration with José Carlos Díaz Ramos and Miguel Domínguez Vázquez. And apart from the homogeneous examples of isoparametric hypersurfaces, which are not completely classified, but they are very well understood, we only have inhomogeneous examples of isoparametric hypersurfaces in complex hyperbolic spaces, quaternionic hyperbolic spaces, and in the Cayley hyperbolic plane. These three are rank 1 symmetric spaces of non-compact type. And the thing is that we can extend the examples that we have in the complex hyperbolic spaces and in the quaternionic hyperbolic spaces to higher rank symmetric spaces. I will not enter into detail in this extension procedure, but basically you can extend the inhomogeneous examples that you have in here to higher rank symmetric spaces. The thing is that the class of symmetric spaces where these inhomogeneous examples and the extension of this inhomogeneous example exist is not a broad class inside the whole class of symmetric spaces of non-compact type. Let me try to be more precise about that. We can associate a diagram with nodes and arrows to each symmetric space of non-compact type. This is the so-called Dinkin diagram, and I will say something else about it later. The thing is that once you have this diagram associated to each symmetric space of non-compact type, you can distinguish between symmetric spaces by looking at the type of different Dinkin diagram that they have. The thing is that, let's say that we have 10 different types of Dinkin diagrams. However, the class of symmetric spaces where these inhomogeneous examples of isoparametric hypersurfaces or their extensions exist correspond to symmetric spaces with just this one Dinkin diagram, BCR Dinkin diagram. So one type out of 10, let's say. And here is the result that we have proved some months ago. It says the following. It says that each symmetric space of non-compact type and rank greater or equal than 3 admits inhomogeneous examples of isoparametric hypersurfaces with non-austere focal submanifold. They are constructed around a non-austere focal submanifold. And indeed, we have infinitely many examples if the rank is greater or equal than 4. And well, there are three things that I would like to emphasize about this result. The first one is that these are, to our knowledge, the first examples in any Riemannian manifold of an isoparametric family of hypersurfaces which is constructed around a focal submanifold which is not austere. Of course, it has to be minimal, but in this case, it's not austere. Also, these examples exist in any symmetric space of non-compact type, just provided that the rank is greater or equal than 3. But it doesn't matter the type of the linking diagram that we have. So they exist in any symmetric space of non-compact type, just provided that the rank is greater or equal than 3. And the last thing is maybe just a curiosity, but I like it, which is the following. Our construction method also holds in reducible symmetric spaces. So if we take the product of 3 real hyperbolic spaces, this is a reducible symmetric space of non-compact type of rank 3. The thing is that in each factor, all the examples of isoparametric hypersurfaces are homogeneous, as follows from this classification due to Elie-Cartan that I showed you at the beginning. However, in this product, we are able to construct an inhomogeneous example of an isoparametric family of hypersurfaces. Well, this is the result, and now I will try to give you some hints on the proof. But before doing that, I need to establish some notations, some tools related to the algebraic structure of symmetric spaces of non-compact type. So this is what
Victor.
Yes.
Before you continue, the F, curvature, and I forgot the names. The examples that are inhomogeneous on spheres.
Yes.
In which dimensions do they occur to begin with? No need to go back. Don't need to go back. Just yeah, okay. What in which dimension do they occur?
I think this, I'm not sure about that. I should probably revise the papers about that. I remember that the remaining case here, that the complicated case here, was in a sphere of dimension 32, I think. I remember that the remaining case, the one which was the last one in getting solved, was with multiplicities 7, 7, 8, 8. But then you have a list of possible multiplicities. This is how I think they got to the problem. You have a list of multiplicities and you just have to check in which dimension that occur. But I don't remember now exactly in which cases do you have.
So the most likely your example is of lower dimension, right? 6. I mean, it seems like
the examples that
very low dimension. Yes.
No,
it's an inhomogeneous.
Because our examples, you can get examples of the dimension that you want with our method. Just you can increase. I mean, if you mean the
yeah. But of course, my point is that these are lower dimensional examples, which is more interesting, perhaps, for as a selling point. That's what I meant. That this happens in dimension 6 already is quite surprising, I would say.
Yes. I see your point. Yeah. I'm not sure about the lowest case in spheres. I'm not sure now. I should check the. I'm not sure. But I'm not sure. I should get to the papers to make sure which is the lowest dimension example that they have. But yes, we have examples in dimension 6. That's true. I will then continue. If okay, as I said, I would like to introduce and to establish some notations concerning the algebraic structure of symmetric spaces of non-compact type. So let M be a symmetric space of non-compact type, and let G be the connected component of the identity of its isometry group. And by K, I will denote the isotropy group of the point O, which is an arbitrary point, but that will be fixed from now on. And I will refer to it many times, probably as the base point or something like that. The thing is that M turns out to be diffeomorphic to this coset, to G over K. And now we can consider the Cartan decomposition of the Lie algebra of the isometry group. We can express it as a direct sum of this Gothic K, which is the Lie algebra of the isotropy group, and P, which is the orthogonal complement of K in G with respect to the Killing form, which is non-degenerate because G is a real semi-simple Lie algebra. Indeed, using the Killing form, it is possible to define an inner product in the Lie algebra G. This inner product makes the Cartan decomposition an orthogonal decomposition. And now we select A maximal abelian subspace of P. The dimension of this maximal abelian subspace coincides with the rank of the symmetric space. And we now consider this family of operators, the family of adjoint operators by elements in H. Well, they are self-adjoint operators with respect to the inner product we have just defined, and they commute to each other. So they diagonalize simultaneously, and we can decompose G, the Lie algebra of the isometry group, as a direct sum of these common eigenspaces. This is the so-called root space decomposition, and each one of these spaces I have in here is called a root space. Here is the definition of each one of them, where this lambda is, of course, an element in the dual space of A, of this maximal abelian subspace that we have selected. And I will denote by sigma the set of roots, that is, the set of covectors of A, such that whose corresponding generalized eigenspace is different from 0. Indeed, one can define, and I will use this map many times later, you can define a map from the dual space of A into A and send each covector lambda in a vector H lambda that satisfy this relation that I have in here. So this is an isomorphism of vector spaces. And since here you have an inner product, you can copy this inner product here. And at the end, you have an inner product in the set of roots. And let's say that you have here in these vector spaces where your roots live, you have kind of a dual version of the roots here in A. Well, the thing is that if one covector is a root, then its opposite is also a root. So this allows to think of a notion of positivity. Basically, what we want is that if you have a root and its opposite, you want one of them to be positive and the other one to be negative. And also you want the sum of positive roots to be a positive roots. So what you can do is to take a hyperplane in this dual space, not containing any of the roots, and just say, okay, the roots that lie above the hyperplane, they will be positive. And the roots lying below the hyperplane, they will be negative. And with this notion of positivity in the set of roots, you can define M as the sum of root spaces associated with positive roots, which turns out to be an nilpotent Lie algebra. And then you get the Iwasawa decomposition at the Lie algebra level, which says that each element here in the Lie algebra of the isometry group can be written as an element in K, a compact Lie algebra, plus an element in A, the abelian Lie algebra that we have selected in here, and an element in this nilpotent Lie algebra we have just defined. Moreover, A plus N is a solvable Lie algebra, so it makes sense to take AN, the connected Lie subgroup of G, whose Lie algebra is precisely this one. The thing is that there is a diffeomorphism between our initial symmetric space and this Lie group, this solvable Lie group AN. So with a pullback of the metric, what we are doing is to identify our initial symmetric space with a solvable Lie group. And indeed, the metric turns out to be left invariant here. And this is, I think, an important tool when one is working with symmetric spaces of non-compact type, because let's say that all the geometric information of your symmetric space of non-compact type can be somehow rewritten in terms of Lie algebras. For example, the inner product can be rewritten in terms of Lie algebra, or the Levi-Civita connection can be rewritten in terms of Lie algebras. And well, for the sake of completeness, I would like to say something about the linking diagrams. So recall that we have a notion of positivity in the set of roots, which means at the end that we have positive roots and negative roots. Well, a positive root is said to be simple if it cannot be written as the sum of positive roots. And using the simple roots of the root system, it is possible to construct the so-called linking diagrams. Roughly speaking, the process goes in this way. We associate a node to each simple root. So alpha 6 is a simple root, alpha 5 is representing another simple root, and so on. And now two nodes are connected if the sum of the corresponding simple roots is also a root. And the number of edges connecting two nodes codifies the relation between the lengths of the corresponding simple roots. At the end, if you have an irreducible symmetric space of non-compact type, then its linking diagram must adopt one of the configurations that I have in here. These are all the possible configurations for the linking diagram of an irreducible symmetric space of non-compact type. And what I was saying a few minutes ago is that before our result, all the inhomogeneous examples of isoparametric hypersurfaces that we knew in symmetric spaces of non-compact type happen in symmetric spaces of non-compact type with this linking diagram that I have in here, this BCR linking diagram. Now, after our result, we have examples in all symmetric spaces. Just we need rank greater or equal than 3, but it doesn't matter the linking diagram that they have. Of course, we do not have examples in this one, in symmetric spaces whose linking diagram is G2, because here the rank is exactly 2. So let's say we don't have enough space here to construct our examples. But in all the rest, we have examples. Well, and then here is the general approach to construct these new examples of inhomogeneous isoparametric hypersurfaces with non-constant principal curvatures that I have been promising from the beginning of my talk. So in order to do so, we will make extensive use of the solvable part of the Iwasawa decomposition that I have just presented. That is this abelian Lie algebra A and this nilpotent Lie algebra N that can be expressed as the sum of root spaces associated with positive roots. Now we will take B, a linear subspace in A, and we will define this letter Gothic S to be the sum of B and the nilpotent part of the Iwasawa decomposition. This set turns out to be a Lie subalgebra of A plus M, so it makes sense to define S as the connected Lie subgroup of AN, whose Lie algebra is this set that we have just defined. And we will consider the orbit of S through the point O. This is, let's say, the base point of the Iwasawa decomposition, or if you prefer, the point whose isotropy group we have utilized in order to describe the symmetric space of non-compact type as a quotient of Lie groups. And well, we can do the following identifications. We can identify the tangent space to this orbit at the point O with the Lie algebra S, and we can identify the normal space to the orbit at the point O with B perp, which is just a notation that I'm using for the orthogonal complement of B as a subspace of A. The thing is that, as I said, I want this orbit to be my candidate for the focal submanifold of an isoparametric family of hypersurfaces. So there are two remarks in here. The first one is that the focal submanifold, by definition, must have codimension greater than 1. But since the definition of this orbit depends on a choice on an arbitrary linear subspace of A, what I will do is to take linear subspaces in A of codimension greater than 1. In this way, this orbit, this homogeneous submanifold, will have codimension greater than 1, as we want. And the other remark is that according to the result due to Ge and Tang that I showed you at the beginning, the focal submanifold of an isoparametric family of hypersurfaces should be minimal. So next step is to study the extrinsic geometry of this orbit in order to understand in which cases or in which extra circumstances this orbit is a minimal submanifold. And indeed, since it is a homogeneous submanifold, we will just study the minimality at the point O where we have these identifications. And here are the tools in order to address this study. Nabla will be the Levi-Civita connection of our symmetric space of non-compact type, which is now identified with a solvable Lie group endowed with a left invariant metric. Psi will be an arbitrary unit normal vector to the orbit at O. So according to this identification, we can and we will assume that Psi is in B perp, the orthogonal complement of B in A. And by A Psi, I will denote the shape operator of the orbit with respect to the unit normal vector Psi. So applied to a tangent vector to the orbit is nothing else but the opposite to the tangent projection of the covariant derivative of this unit normal vector Psi with respect to this tangent vector x. And I will not enter into more detail here, but this is the explicit determination of the shape operator of the orbit. So the thing is that if we take h in the abelian part of the tangent space to the orbit, these are eigenvectors of the shape operator, and the associated eigenvalue, the associated principal curvature, is 0. This is somehow reasonable because if you take the connected Lie subgroup of AN whose Lie algebra is A, then the orbit is totally geodesic. The orbit through O is totally geodesic. So as a geometric interpretation, we can say that this orbit that we are considering has a totally geodesic region, the region corresponding to the abelian part of the tangent space. So now we have analyzed the abelian part of the tangent space. Let's go with the nilpotent part of the tangent space that can be decomposed as a direct sum of root spaces associated with positive roots. So I will take directly x alpha in G alpha, which is the root space of a root alpha. It is also an eigenvector of the shape operator of the orbit, and here is the principal curvature that we have. Is alpha, which recall is a covector of A, an element in the dual space of A, applied to psi, which is an element in B perp, which is in A. So it makes sense. And well, if we want our orbit to be minimal, we will compute the mean curvature vector with respect to psi, which at the end is the trace of this shape operator. So this abelian part of the tangent space does not really play a role because all the principal curvatures are 0. And here we can interpret that part in the following way. For each positive root, we have a principal curvature. And this principal curvature will appear as many times as dimension we have in the corresponding root space. So here what I'm writing is the principal curvature and its multiplicity. And now I will use this kind of identification that we have between roots and its dual version in A to substitute. Instead of applying alpha to psi, I will write here H alpha and psi. So I'm just using this property. And now I will use the linearity of the bracket product, and I will include this sum in the first member here. Note that this element that we have in here, since this H alpha, they all belong to A, this is an element in A that I will call with this strange letter H. The thing is that we want this orbit to be the focal submanifold of an isoparametric hypersurface, of an isoparametric family of hypersurfaces, so it has to be minimal. So we need this inner product to be 0 for any unit normal vector psi that we have in here. But this is an element in A, and let's say that we are taking an arbitrary linear subspace of A of codimension greater than 1. So what I will do is to make another imposition on B. I will say that H is always in B. I will take B in such a way that H is in B. In this way, H will be identified with a tangent vector. And then here I will have the inner product of a tangent vector with a normal vector. So this will be always 0. And then this submanifold is going to be minimum. So as a summary to this slide, what I'm saying is that if we take B, a linear subspace of A, of codimension greater than 1, and containing this distinguished vector, which is also the mean curvature vector of N in the symmetric space, then this orbit will be a homogeneous submanifold of codimension greater than 1 and minimal. And this will be our candidate for the focal set of an isoparametric family of hypersurfaces. So,
Victor, I think there's a geometric interpretation for your H here. I think that's the mean curvature vector of the nil radical of AN.
You mean that this H is precisely the mean curvature vector of N as a submanifold of the whole symmetric space?
Yes.
That's true. Indeed,
yeah,
if I'm not mistaken, I think that including H here also guarantees that if the ambient symmetric space is Einstein, this submanifold is also Einstein.
Precisely, yeah, that's the condition.
Okay, thank you very much. Well, as I said, the next step consists in constructing tubes around this orbit and trying to check or to see that they are indeed examples of isoparametric hypersurfaces. So let's go. At the top of the slide, I'm just recalling the main ingredients to construct this orbit. So be a linear subspace in A of codimension greater than 1 and containing this distinguished vector H. And now we will construct use around this orbit. Indeed, by MT, I will denote the tube of radius T around the orbit. Here is the precise definition. Basically, we are exponentiating the unit normal bundle of the orbit at a certain distance, at distance T. Indeed, I think in this picture, it's quite clear what is happening. This black straight line that I have in here is playing the role of our orbit. So at each point of the orbit, we are considering all the unit normal vectors. So these red vectors that I have in the picture, we are throwing geodesics in the direction of all these unit normal vectors, and we are evaluating all these geodesics simultaneously at time t. What we have is this green surface, but let's say that in the theoretical case, we get a tube, a hypersurface. Of course, we have to prove that. We do that in terms of Jacobi vector fields, and I will say something else about that later, but let's assume that this is a hypersurface. Next step will be to understand the geometry of this hypersurface in terms of the geometry of the orbit. So let me try to explain what is happening here with a very simple picture in R3, let's say. So this blue straight line is our orbit, the orbit of S to the point O, and this black cylinder will be the tube of radius T around the orbit. So I will denote it, as I said, with MT. The thing is that if we fix a point P in the tube, then by definition, there must exist a point in the orbit and a unit normal vector to the orbit at this point, psi, in such a way that if we throw a geodesic gamma starting at this point and with this initial direction, gamma will reach the point P at distance T. So P is at the end gamma of T. And also, since this orbit is homogeneous, we can and we will assume that this is the base point of the Iwasawa decomposition. And let me also emphasize something which will be important later, which is that at the end with this interpretation, what I'm saying is that each point P in the tube is somehow determined by the choice of a unit normal vector to the orbit at the point O. And well, now let's try to understand the tangent and the normal space to the tube at P by means of the tangent and the normal space to the orbit at O. The thing concerning the normal space, the thing is that this geodesic intersects all the intermediate tubes. I mean, here we have a lot of intermediate tubes, those of radius between 0 and T. And this geodesic intersects all of them and all of them orthogonally. So if we take the derivative of gamma at T, we get a unit normal vector to the tube at the point P. And since if you fix one point in a hypersurface, then up to sign you just have one unit normal vector. Let's say that we understand the normal space to the tube at the point P. What about the tangent space? Well, if we take here this purple vector, which represents a vector which is tangent to the orbit at O, and we consider the parallel translation of this vector along gamma until distance T, then we get a vector which is tangent to the tube at P. So let's say that the parallel translation of vectors which are tangent to the orbit give vectors which are tangent to the tube at the point P. And now, imagine that we take this yellow vector, which is a vector which is normal to the orbit at O, but also normal to this unit normal vector psi, which determines the point P. If we consider the parallel translation of this vector along this geodesic until distance T, then we get a vector which is again tangent to the tube at P. What I'm trying to explain with this picture is that at the end, the tangent space to the tube at the point P, and recall that the point P is determined by the unit normal vector psi, the tangent space of the tube at the point P consists of the parallel translation of vectors which are either tangent to the orbit or normal to the orbit, but also normal to this unit normal vector which determines the point P. Of course, this is just a very brief idea in R3. What we really have to do here is to use Jacobi vector field theory. We take X, which is in the sum of these two vector spaces, the tangent space to the orbit at O, and also the set of normal vectors to the orbit at O, which are also normal to psi. And then we construct a Jacobi vector field associated to X, that is associated with X, that is a solution of the Jacobi equation, this ordinary differential equation that I have in here, and we impose these initial conditions. Jx as 0 should be the tangent projection of X with respect to the orbit, and the covariant derivative of Jx as 0 should be the normal projection of X with respect to the orbit minus the shape operator of the orbit applied to the tangent projection of X. These Jacobi vector fields are usually called adapted Jacobi vector fields. And the thing is that in order to prove that MT is indeed a hypersurface, you have to study the dimension of this span that I have in here. But once you do that, let us assume that we have a hypersurface, you can see that the tangent space of the tube at the point P is the span of these adapted Jacobi vector fields evaluated at T, where this X varies in a basis of this vector space. And indeed, using Jacobi vector field theory, Jacobi field theory, we can also determine the shape operator of the tube. Here I have the equation. By AT, I mean the shape operator of the tube of radius T around our orbit. Of course, it is calculated with respect to a unit normal vector, as it is the case of the derivative of gamma T. And since we have this identification of the tangent space, we can apply it to one of these adapted Jacobi vector fields. What we get is the opposite to the covariant derivative of these Jacobi vector fields evaluated at T. Well, so I will not explain how to obtain these Jacobi vector fields, but I will still use their explicit expressions to calculate the shape operator and to deduce the principal curvatures in order to show you that these tubes are indeed examples of isoparametric hypersurfaces. So as before, at the top of the slide, I'm just recalling some of the facts that we will use now. Here are the initial conditions. Here is the expression of the tangent space, and here I have the equation of the shape operator of the tube. We want to show that this tube is isoparametric. So here I recall the definition of isoparametric hypersurface. An isoparametric is said to be, a hypersurface is said to be isoparametric if it and its nearby equidistant hypersurfaces have constant mean curvature. So since we are in a hypersurface, I will identify the mean curvature with the trace of the shape operator. And since this T is an arbitrary parameter, what I will try to see is that this tube has constant mean curvature, which is the same of checking that the mean curvature of this tube at P does not depend on the point P. But recall that this point P is determined by the choice of a unit normal vector psi. So what we really do is to see that the mean curvature or the trace of the shape operator of this tube at the point P does not depend on this unit normal vector psi determining the point P. So I will then show you the explicit expression of the Jacobi vector fields, and then using the equation of the shape operator, we will be able to deduce the principal curvatures of the tube at the point P. So here is just the tangent space to our orbit. If we take a vector in the abelian part of the tangent space to the orbit, you can see that, of course, the tangent projection will be H itself, the normal projection will be 0, and since it is in the abelian part of the tangent space, this will be also 0 because they were eigenvectors of the shape operator of the orbit with associated eigenvalue 0. So at the end, these adapted Jacobi vector fields are the parallel translation of H along the geodesic. So using this expression, you can see very easily that this is then an eigenvector of the shape operator of the tube with associated eigenvalue, with associated principal curvature 0. So I will write 0 here in the trace of the shape operator of the tube. I will not enter in so many detail for the rest of the Jacobi vector fields, of the adapted Jacobi vector fields, but if we take now a vector x alpha in the nilpotent part of the tangent space to the orbit, here is the adapted Jacobi vector field that we get. Again, using this equation for the shape operator, it is very easy to see that this is an eigenvector of the shape operator of the tube, and the associated eigenvalue, the associated principal curvature, is again, alpha of psi. Recall that this is a covector in A and this is a vector in A. And each one of these principal curvatures will appear as many times as dimension we have in the corresponding root space. And finally, we will take eta, a vector which is normal to our orbit, but also normal to the unit normal vector psi, which determines the point P. And here, the adapted Jacobi vector field is directly T times the parallel translation of eta. Again, using the expression of the shape operator, it's very easy to deduce that it is an eigenvector of the shape operator with associated eigenvalue, with associated principal curvature 1 or minus 1 over T. And here is the multiplicity. So here is the trace of the shape operator of the tube. And I said that we have to see that it does not depend on psi. And here it seems that it depends on psi. But what we have here is again the same calculation we had for the orbit. This is the inner product of the distinguished vector h, which is always tangent to the orbit, with a unit normal vector psi. So this will vanish, and at the end, the mean curvature of the tube of radius t is this one. So of course it depends on the radius of the tube, but is constant for one tube. So what we have proved is that the tubes around the orbit we have just constructed are indeed examples of isoparametric hypersurfaces. And well, at the beginning, I said that I was going to construct new examples of inhomogeneous isoparametric hypersurfaces with non-constant principal curvatures around a non-austere focal submanifold, and that these examples will hold for any symmetric space of non-compact type of rank greater or equal than 3. So far, we have examples of isoparametric hypersurfaces. They hold in any symmetric space of non-compact type and rank greater or equal than 3. This is something that we have done. But I did not say anything about the fact that they are inhomogeneous, about the fact that they have non-constant principal curvatures, or about the fact that they are constructed around a non-austere focal submanifold. So now, and in order to simplify this last part of the talk, I will just give a hint on how to prove that in general, these examples are constructed around a non-austere focal submanifold. And then these two things can be deduced from the result due to Guéhentin, because if we have examples with constant principal curvatures, as will be the case if they were homogeneous, then they will be constructed around a CPC submanifold, which is always austere. So I will try to show you that, or I will try to give a hint on how to show that in general, our examples are constructed around a non-austere submanifold. So as usually, here I just recall the main ingredients to construct the focal set. And here I have the principal curvatures of the orbit with respect to a unit normal vector psi. We have 0 as a principal curvature, and then let's say that for each positive root, we have a principal curvature. Indeed, this last part allows to interpret principal curvature with positive roots and then with linear functionals on the normal space to the orbit. And recall also the definition of austere submanifold. A submanifold is said to be austere if its multiset of principal curvatures is invariant under a change of sign. So this means that if you have an austere submanifold and you have a non-zero principal curvature, the opposite number should be also a principal curvature. So combining these two ideas, this idea following from the definition and this interpretation of principal curvatures as positive roots, what I'm saying is that if the orbit that we are considering is austere, then if we have a non-zero principal curvature, it is induced by a positive root. So I will need another positive root inducing the opposite principal curvature. So a way of writing down what I have just said is that our orbit is going to be austere if and only if there exists a permutation sigma in the set of positive roots such that for each positive root lambda, and applying the permutation to lambda, vanishes when applied to the normal space to the orbit. What I'm saying basically is that lambda and sigma of lambda, they are induced opposite principal curvatures. And again, using this relation that we have, this relation that we have between roots and its dual version, the orbit is going to be austere if and only if there exists a permutation such that this element that we have in here is normal to the normal space of B perp. So if this element belongs to B for any positive root lambda. So here there is an equivalent claim for this orbit to be austere. But we want is to have a non-austere orbit. So what we do is the following. We prove that in any symmetric space of non-compact type and rank greater or equal than 3, we are able to find a positive root such that any member of this finite set is not collinear to the vector h, which is this distinguished vector, which is always tangent to our focal submanifold. And now what we do here is to select B a subspace of A of codimension greater than 1 and containing this vector h, but not containing any of the vectors of this set. In this way, what we do is to guarantee that in this submanifold, alpha will induce a principal curvature whose opposite is not going to be a principal curvature. And there is an important remark that I would like to do here, which is that I'm not saying that all the examples that we construct are around a non-austere submanifold. What I'm saying is that we are able to construct infinitely many around a non-austere submanifold, but we also have examples around austere submanifolds. And since I think I should maybe stop, I will finish with a maybe more detailed version of our main theorem. We are in a symmetric space of non-compact type and rank greater than 3. Here is the trick at the Lie algebra level, taking B a subspace of A of codimension greater than 1 and containing the indistinguished vector. We then take S, the connected Lie subgroup of AN, whose Lie algebra is Gothic S, and the orbits through O are always minimal submanifolds, which are non-austere for a generic choice of B. By generic choice, I mean an open subset in a Grassmannian. The thing is that the distance used around this orbit are inhomogeneous examples of isoparametric hypersurfaces with non-constant principal curvatures. And also, after studying the congruence, we can guarantee that we have infinitely many which are non-congruent. And well, I think that I will then stop here. Thank you for your attention.
Yeah, many thanks, Victor. Very nice talk. Are there any questions for the speaker? Comments? I do have some questions, but I'll let Yuri ask first.
Me? Ah, thank you, Victor. Excellent talk. I was just wondering if you can, well, I understand in this particular case, you can just solve the Jacobi equation explicitly and write down your Jacobi fields and compute your curvatures. But just if you take this solvable algebra, solvable group not coming from symmetric space, just you have nil radical and a nice bunch of commuting derivations, will you be able to use your construction, similar construction?
I'm not sure about that. That's yes, that's probably the next step I should try, but I didn't try yet. I'm not sure. Yes, the Jacobi equation in this case is very simple, and indeed is an indication in the book of Everlane how to get these Jacobi vector fields. But I'm not sure what is going to happen if you just refer to a general solvable algebra with an radical. I'm not sure. That's probably the next step I should try to understand if these examples can be generalized to this case. But I don't have
There's
an
some, I mean, I wouldn't try to do it in full generality, but there's some called Iwasawa type solvable algebras that share a lot of properties, you know, this sort of simultaneous diagonalization and maybe.
Yeah, I know about this Iwasawa type algebras, and maybe it's a good starting point. And I know that they play an important role when studying Einstein submanifolds and so on. So yeah, probably a reasonable next step is trying to understand if in a Iwasawa type Lie algebra, solvable Lie algebra, you can do something like that. But I don't know. I don't have an answer yet.
Thank you, Victor.
There's a question by Sebastian Bolt in the chat. So how do we know that the MT are submanifolds?
Yes, that's that's
valid question.
A very reasonable question. What you have to do basically is, well, I did not enter into detail in that part, but you can define a map from this unit normal bundle of the orbit to your symmetric space of non-compact type. And you will be able to see that this map has a constant maximal rank. So basically this will give you that you have a hypersurface in the ambient symmetric space of non-compact type.
So I was wondering, Victor, how does one show that these things are inhomogeneous? Because they do admit an action of S, right? But apparently the compact quotient, I mean, it's not homogeneous. Is that what happens?
The easiest thing is because we are able to compute explicitly the principal curvatures, and we see that they have non-constant principal curvatures, so they cannot be homogeneous. That's the way we do that. But I don't know, maybe there's another way that these examples can be viewed. I decided not to include that in the talk, but I think I have a slide about that. The thing this will take 5 minutes, I'm sorry for that. But another funny way of showing what you say is the following. These examples can be regarded from a different point of view. So I need just to say that what a polar action is. If you have an isometric action and there is a submanifold that intersects all the orbits orthogonally, then it is said to be a polar action. The thing is that the group S that we are considering to construct our orbit, it acts freely and polarly on the symmetric space of non-compact type, and the section, which is always in a polar action totally geodesic, in this case is also flat, so it is isometric to a Euclidean space. And the orbits of our action...
It's hyperpolar then. Right?
Yeah, exactly. It is hyperpolar. And the orbits of our action are mutually congruent and minimal. So the picture that I have in mind is that this plane that I have in here is the section, and then all the orbits of the action intersect this plane. The thing is that we have an extension method that allows to extend some manifolds from the section to the whole symmetric space of non-compact type. The idea is very simple. If you have a submanifold P in the section, this is playing the role of the section, what you do is to attach all the fibers through points of the submanifold. And what you get is this submanifold in the ambient space. The thing is that this method, this extension method, preserves isoparametricity, but not homogeneity in general. So we can extend isoparametric hypersurfaces that live in the section, but this section is a Euclidean space, so we can extend isoparametric hypersurfaces from Euclidean spaces, and we have a classification. So we can extend the examples of isoparametric hypersurfaces that we have in the Euclidean space. The thing is that the examples I have presented, they are the extension of spheres in the section. So isoparametricity is preserved, but not homogeneity. We can see that homogeneity is only preserved if you extend hyperplanes. So this is another way of answering your question. These examples are not homogeneous because they are the extension of spheres in a Euclidean space, and here homogeneity is not preserved. It's only preserved if you extend hyperplanes.
I see. Interesting. Maybe my final very quick question for the future. If any of these hypersurfaces is Einstein, then I will be very interested in seeing this example. Not the focal one, right? The other one.
Yeah.
But this is for not for now, but just for you guys to think about that. I expect them not to be, but we don't know.
I'm not sure, but indeed I am. One thing I'm starting to do is to think about Lie subgroups of symmetric spaces which are Ricci solitons. So of course, just
but here
Lie
I'm talking
subgroups,
about
not
the
all the
inhomogeneous
hypersurfaces.
one.
Sorry.
I'm talking about the inhomogeneous ones, right?
Yeah.
The
But I mean,
cubes.
I don't have an answer. I'm just saying that
No,
I'm
no,
starting to think about these kind of things, but I don't have an answer for that, and I don't really know if they will be or not Einstein.
Okay.
I'm not sure. That's a good question.
Einstein, they must be. I think they must be homogeneous if they're Einstein.
They must be because it's homogeneous co-dimension one. I see.
Yeah.
I see. Yes. Well, thanks. That's what I expected. But would have been interesting. All right, Victor. Then, if there are no more questions for the speaker, we can thank him again for a very nice talk.
Thank you.
Yeah, very clear, extremely clear, I would say. I really enjoyed it. Let's stop the recording.